And I am live. That is cool. So today is 15th of September 2025, Monday, and today we are going to complete the last section of dynamic programming from the CLRS book. So let's just begin. Yep. Here is the thing, and today is literally the last section. So optimal binary search trees. I do know about binary search trees. We did a stream in which we implemented a binary search tree on our own from scratch. So that was cool. And yeah, this is the last section. And after this section, there will be some exercises. These will be about binary search trees. So that would be cool. And then and then there are problems for the chapter itself. And this one is about graphs, longest palindrome subsequence. That is going to be cool. I think that might be one of the questions in CACS. And yes, when we are done with this whole dynamic programming thing from CLRS book, then we will go through all the dynamic programming questions in this CACS. So that would be cool. Palindrome. Okay, so there is no palindrome question here. Counting tiles. I do not know how to do counting tiles, and it is going to be pretty cool to get to know that. But with all the tools that we have gathered till this point in dynamic programming, I think we are pretty well off compared to where we were uh, only 3 to 4 days ago when we began solving all of these questions. And one of the things uh, we know is there are 4 steps in dynamic programming. First is define an optimal solution. That is the first step, how an optimal solution would be like, what it would look like. Then recursively define optimal solution using optimal solution to subproblems. So that is the second step that we have to do. And then there is the third step, which is like most of the times, which is the last step, and that is find the optimal value for the answer. So in most of the questions, third, second, and third, these are the steps that we have to do in most of the questions. But in some questions, we also have to return the optimal solution which gave this optimal value. So construct a optimal solution. And there is a difference between the optimal value and the optimal solution. Because, for example, if you are doing the coin change problem, then in that, if you want to find out the minimum number of coins required to get to a sum, then the optimal value would be the number of coins required to get to that sum, and an optimal solution would be the sequence of coins that you must take to get that optimal value. So there is a distinction between the solution and the optimal value. And this optimal value might come from one of the solutions, or there might be multiple solutions which can give that optimal value. So that is why I have written here construct a optimal solution, not the optimal solution, because there might be multiple optimal solutions giving the same optimal value. So those are the 4 steps that we have to do. And then there are a couple of things. There are like choices. At every recursive step, we have a choice. And we do not know, we assume that among these choices, one of the choices is going to be the optimal choice. And generally, it is unknown beforehand which choice is better. Therefore, we need to literally make those choices and find out the value, the optimal value, the optimal value that we could get as a result of making those different choices. And that could mean something like, if you make choice 1, you get some optimal value, let's say A, and if you make some choice 2, you get some optimal value B, and yeah, so depending on the number of choices, you will get different optimal values as a result of making those choices. And you can, you have to see all of these optimal values which you get as a result of making those different choices and compare. And if you want to find the minimum optimal value, if you are defining the optimal value as the minimum value, then you take the value that is minimum and go with that choice. But if you want to find out the maximum value and you are defining your optimal value as the maximum value, then you take the maximum value among all the choices. And these values themselves, A and B, which you get as a result of making a choices, depends on two things. So value of a choice. So first part is optimal value for the dependent subproblems, right? May as a result of making these choices, making a choice, your result would depend on a set of subproblems that you would have to solve if you are making a certain choice. And the value for making this choice would be the sum, or sometimes sum, sometimes subtraction. It depends. It actually depends on the kind of the problem that you're trying to solve. But generally speaking, the value of a choice depends on the optimal value returned to you by the subproblems plus the inherent value of making that choice. That is the second thing that the value of the choice depends on. And these are like very abstract things and they don't mean a lot without examples. So while we do solve some questions, it would be easier to judge from them what these things mean. And that is not kind of it, but those are the main things we have to keep in mind while solving a dynamic programming question. These are the 4 steps. At each step, we have some choices, and some choices have some values, and we compare the values and find the choice that is the best one. And how do we find the value of a choice? By finding optimal value for the subproblems plus key weight. My bad. So how do you find it? And is my camera still working? Yes, my camera is still working. That is cool. That does work. And yeah, value of making a choice, optimal value for the dependent subproblems, and inherent value of making that choice. Those are the things that the value of your current choice depends on. And now moving on to this thing, optimally traversing a binary search tree. I mean, I don't know. I guess already optimal binary search tree. I don't know how you would optimize binary search trees because the search time, insertion time, deletion time is already log n. So I don't know, Latvian equivalent, Latvia, what Riga. Suppose that you are designing a problem to translate text from English to Latvian. Okay. For each occurrence of each English word in the text, you need to look up its Latvian equivalent. You can perform these lookup operations by building a binary search tree with n English words as keys and their Latvian keys as their Latvian equivalents as satellite data. Because you will search the tree for each individual word in the text, you want the total time spent searching to be as low as possible. You can ensure and log in search time per occurrence by using a red-black tree or any other balanced binary search tree. Words appear with different frequencies, however, and frequently used words such as the can end up appearing far from the root, while a rarely used word such as naumachia appears near the root. Such an organization would slow down the translation since the number of nodes visited when searching for a key in a binary search tree equals 1 plus the depth of the node containing the key. You want words that occur frequently in the text to be placed nearer the root. Okay, that is something that you could want if you are like searching for a lot of words in your BST. Moreover, some words in the text might have no Latvian translation, and such words would not appear in the binary search tree at all. How can you organize a binary search tree so as to minimize the number of nodes visited in all search, given that you know how often each word occurs? That is a very interesting question. That is actually a very interesting question, how you would do something like that. And what you need is an optimal binary search tree. Okay, that is, I'm already scared. Formally, given a sequence k equals something of k1, k2, kn, of n distinct keys such that, okay, they are in sorted order, build a binary search tree containing them. For each key ki, you are given the probability pi that n given search is for k key ki. Since some searches may be for values not in k, you also have been given n plus 1 dummy. Since some searches may be for values not in k, you are also given n plus 1 dummy keys representing those values. Okay, so we have these keys which have their values, their Latvian equivalent values, and then we have some dummy keys which do not have any Latvian equivalent. In particular, dx0 represents all values less than k1 and dn represents all values greater than kn. Okay, so they are in a, okay, and for I equals 0, for I equals 1, 2, 3, 4 till n minus 1, the dummy key di represents all values between ki and ki plus 1. For each dummy key di, you have the probability qi, that is a search corresponding to di. Figure 14.9 shows how two binary search trees for a set of n equal to 5 keys. Okay. Each key ki is an internal node. In this tree, we have two trees. One is for the actual values, for the keys which do have some actual values. No, shit. No. We have stuff that is scattered. Okay. The actual keys and dummies are scattered. That makes a lot of sense. Here we have all the null values. Leaves have d0, d1, d2, d3 as their children, because that is how these keys d0, d1 till dn are defined. That is actually very smart. Yeah, that is actually pretty smart. So figure 14.9 shows two binary search trees for a set of n equal to 5 keys. Each key ki is an internal node and each dummy key di is a leaf. Yes, each Since every search is either successful, finding key ki, or unsuccessful, finding a dummy key, di, we have, yeah, the total probability is going to be 1. Okay. And if we have n keys, actual keys, whose value we have, then we are going to have n plus 1 dummy keys. Okay, knowing the probabilities, and these are the probabilities for dummy keys. And why do we have two search trees here? Two binary search trees for a set of n equals to 5 keys with the following probabilities. These are the probabilities, and these are the equivalent trees that we can build. Contribution, depth are different in both the key in both the trees, and also probability is the same, of course. But contribution, how do you define a contribution? Knowing the probabilities of searches for each key and each dummy key allows us to determine the expected cost of a search. Ah, expected cost. Yes. So we would like to minimize the expected cost, I guess. Expected cost of a search in a given binary search tree T. Let us assume that the actual cost of a binary search equals the number of nodes examined. Okay, that would be the actual cost, and we multiply that by the probability of how many times that thing is going to be searched for, which is the depth of the node found by the search in T, plus 1. Then the expected cost of a search tree in T is of a search in T is depth of ki, the ith node. Okay, this is the total expected cost. Okay, that makes sense. So for the ith node, we have, yes, yeah, that makes sense. That makes sense. The value multiplied by probability, and we are summing it all. And the same for the dummy nodes, and we are summing it all. Here we have taken I1 outside. And does that make sense? I think it is fine. N into pi, this should be n into pi, I think. N into pi, yeah. Yep, n into pi, but pi is also changing, and sum of pi is not equal to 1. Summation of pi is not equal to 1. Summation of pi and qi is equal to 1. Not pi alone, but we also have qi here. So yeah, we can take this one outside, where depth T denotes nodes depth in the search tree. The last equation follows from equation 14.10. Yeah, this part can be derived from this equation right here, because when we sum all the probabilities, we get 1. And here we have pi n times and qi also. Qi is like summarized n plus 1 times. Therefore, the whole thing is going to be 1 when we sum them. The sum of pi's and the sum of qi is going to be equal to 1. So we have taken these one out. For a given set of probabilities, your goal is to construct a binary search tree whose expected search cost is smallest. Yes, we can call such a tree an optimal binary search tree. Okay, this is starting to make more and more sense. That is nice. Hello. Should I first complete sheet and then solve random problems, or should I do it after completing each topic of DSA from sheet? Okay, in the sheet, uh, the problems are not topic wise, they are rating wise. And like your main goal is not to complete the sheet, but to understand the things there that are in the sheet. And so while you are solving a question, you can see what the topics were involved in that question and then become comfortable with those topics. That should be the goal. Could you just share what resources you follow in this series? Like these are the things for reading. For okay, so there are things have been divided into two parts mainly. There is the theory part for which I am using books. This is one of the books, Competitive Programmer's Handbook. Then there is this book, Introduction to Algorithms. And then there is a website, which is this one, Algorithms for Competitive Programming. And for questions, what else? No, not for questions, but for theory. There are a few YouTube channels which I watch for theory. Ericto, this is one of the YouTube channels that I watch. Like you can see, I watched this video, and the book that he is holding is Thinking in C++, Part 2, which is a nice book. I haven't read it, but I will in due time. So yeah, this is one of the channels. And yeah, that is pretty much it for YouTube channels that I watch for competitive programming. So these things are for theory, Competitive Programmer's Handbook, CLRS. This book is also called CLRS because of the names of the authors, CLRS. And this also for theory and also this for theory. And then for questions, when I want to practice some specific topic, I go onto this website, CSES. It has questions based on topics, sorting and searching, then dynamic programming. And after I read all of this dynamic programming things, I'll be doing all of these questions, which is going to be tomorrow. And then questions about graph and all the things. Yeah. Topic wise. Practice can be done from here. And then there is the CP competitive programmers CP31 sheet. And yep, I do questions from here linearly from easiest to hardest. And right now, I saw that I was struggling a lot in these questions. So I decided to first get really comfortable with dynamic programming. And after I have done that, then I will continue solving these questions. And that would be nice. And during solving sheet, every question has something new. So I do almost all questions while looking at video solution. Is this right? Okay, if okay, so after you watch the video, are you able to understand what was the thing that you didn't know before watching the video, which if you didn't know, you would have been able to solve the question. And if you can figure that out after watching the video, then it is fine because you do not have to invent new algorithms every time that you see a question. Learning is faster, so it is sort of like learning from other people's mistakes. That is good if you are learning. If after watching the video, you are able to implement the solution, then it is good. If you are able to implement the solution after watching the video. But if you are unable to implement the solution or only implement the solution by referring to the video again and again, then it is not so good. And I would suggest if you are watching a video solution, then come back the next day, do not watch the video and write the solution again on your own. And if you can do that, then it is nice. Lead code plus GFG enough for shortlisting at FANG or code forces is needed at least for shortlisting. Okay. I do not know what GFG is, but okay, this is something that people do. I used to do this when I was learning, studying for JEE. I was looking for the best book that I could use for physics or the best book for chemistry, but it does not matter. You are asking, is lead code plus GFG and code forces enough? Have you done lead code? Are you very good at lead code? Can I give you any question from lead code and would you be able to solve it? I guess not. So you haven't even completed lead code yet, and you are asking, is it enough? So I would say any one of these in itself, if you do it, actually do it completely, they would be enough. But the thing is that you would have to do them. So, yep, they are enough. Any one of them is enough. For me, I'm just doing competitive programming from this sheet. And for practice on some specific topics, I go on to here. And that is it. I'm doing in the domain of questions. And that is enough because I'm complementing it with some studying. So that is cool. Are people who are good in maths naturally good at DSA? Y- Yep, I would say they have some inbuilt advantage which they can utilize. But being good at maths is not something that you inherently have. You can develop it over time if you practice. So yeah, I mean, if you work hard, then someone being good at maths won't be able to beat you if they are not working hard. So all of these things are just something that you can develop and not something that you are born with. So you can develop them. Hey, what is this stream about? Hello, this stream on this whole channel is about showing you that you can, mainly the purpose is showing you that you can become really good at anything that you choose if you work hard. And I am being the example here. I am being the experiment here on whom this experiment is being going on. And you can go back. Today is my 77th stream, I think, on competitive programming. You can go back to my first stream on competitive programming and you can literally compare. I was very stupid on that first stream, but now I am much better than I was in the first stream. And by the end of this year, I will, as a matter of fact, reach a rating of 2000 in code forces. And if you go code forces ratings and this one, if you go here at a rating of 2100, only 1.61 percentile. If you have a rating of 2100, you are in the top 1.61 percentile. And I will show you that you can reach it just by sheer working hard plus smart and being consistent. All smart at brain intelligence. It is just about developing it. Yes, that is what my belief is. Yeah, I think it is a learned ability. Damn, amazing, bro. Are we solving an DSA right now? Right now, we are going through theory for binary search tree, optimized binary search tree. And yes, and I am streaming this because if I was not streaming this, I would not go through this because this is hard. This is hard because I would just give up and not do this. So I'm streaming this and I am, you could say, experimenting with myself and experimenting in public. And you can see that I will become better as I go on, and that might actually help you. So I would be happy if I could help you in that way. And yes, I think we are intelligent. We just have to develop it. Because if I compare myself to how I was a few years ago, or even not even few, even just 9 or 10 months ago, I was very bad at everything. My English was bad, and now my English is much better as compared to I was back then. My English is much clearer. I am much more articulated than I was before. Uh, And so DS is the same process as for all, whether it's an IIT or a typical research. Yes, yes, of course. Yes, it is the same thing. If you, it is just about the mindset. A typical, as you are saying, a typical tier 3 guy would think that he is supposed to be a typical tier 3 guy. But if he thinks that he is one of the best and he can become one of the best, then he will become one of the best if he has that mindset. A person going into an IIT has the mindset that he is supposed to be one of the best. So he studies like it. So he studies to be one of the best. So it is just about the mindset. If you think you can become one of the best, you will become one of the best if you put in the hard work. And that is what I'm trying to show with my stream, because I will become really good. I want to become really good. And if I could do that, which I will, which I am doing by being consistent and working hard, if that helps you, it would be pretty cool. And to optimal binary search trees, whatever that is. So we have basic binary search trees, and in a basic binary search tree, we have time for insertion, deletion, and insertion, deletion, and lookup. It takes log n time in a normal binary search tree. But if we know beforehand that some keys, if we know beforehand that some keys have higher probability of being looked up for and some keys have lower probabilities of being looked up for, then what we can do is put those keys higher up, closer to the root, so that when we are looking for keys with higher probabilities, with higher frequencies of lookup, we do not have to traverse through a lot of nodes. Even though the time is log n, the constant log n factor, it would be reduced and it would be pretty good. So that is what we are calling our optimal binary search tree, where the keys who have higher frequency of being looked up, higher probability of being looked up, are closer to the root. So that is a optimal binary search tree, and that is what you will do. How you improve English? Okay, for improving English, you have to do four things, specifically four things. You have to write English, you have to speak in English, you have to listen in English, and you have to read in English. For reading, you can take any novel or book or anything. For writing, you can just take a register and pen and start writing about things, anything. Writing about anything would be good. And then for listening, you can watch English movies, you can watch YouTube videos which are in English. And then for speaking, for actually speaking and practicing, there is a website, maybe you know about this, freefortalk.com, and I have spent on this website hours practicing my English, talking to random people at 2 in the morning. Yeah, so you can go to this website, join any call, and then talk to people in English. And this is not an English specific website. You can learn any language here. You can talk in German if you want. Expand German. There is only a single room in German. No one is there speaking in German. But yeah, this is the website you can use. You can join rooms and you can talk to people and actually talk and improve your English. That is good. And one more thing which has made me believe that brain intelligence is there, so-called brain intelligence is there. All we have to do is unlock it. Is I used to think that I saw a friend of mine who was like, who knew every country in the whole world. If you tell him any country's name, he will be able to tell you where that country is in the whole world. And I thought that that is crazy, that it was very impressive, and that I would never be able to do something like that. But then I practiced, and now I also know names of all the countries in the world and capitals. Yeah, so now I can even do that. And that made me believe if I got better, so much better at something like this, Maybe I can get better at anything I choose if I want to get better. So yeah, that is it. Back to the question. Optimal binary search tree. Figure 14.9a, which is above this one on the left, shows one binary search tree with expected cost of 2.8. Okay, shit. Yes, we can use this formula to find the cost. And why is this formula correct? Let's see why is this correct. The general formula for expected value is something like this. For if we try to draw a graph where on this axis, let's say, we have the values, and then on this axis, we have the probability of getting those values like this. And your probability distribution could be anything. So if you look at this point, then getting a value of this, getting a value in this range has this much probability, whatever this x value is. So yeah, that is our normal probability distribution. But our expected value, when we give it some probability function, this distribution function gives us what would be if you pick any value with these probabilities randomly from the available values that you have, what would be the expected value that you get after you pick any value with this probability distribution, and that is called the expectation function. And how it is calculated is, let's say you have values discrete. Let's talk about discrete probability before moving on to graph, or maybe we won't even move on to graph. Let's say you have a bunch of values. Let's say you have a bunch of values v1, v2, v3, v4, v5, v6, and dot dot dot. And then you also have a bunch of probabilities which are associated with those values, v3, v4, v5, v6, and dot dot dot. If you have that, then the formula for the expected values, and let's say this goes till Vn, and consequently this would go till V till Pn. Then the expected value function would take in this probability distribution, which we are calling x, and this will be equal to summation. I don't know how to make the summation symbol from keyboard, so we will have to work with this summation, and we will have vi I multiplied by pi, not 8 but I, and we have I will go from 1 till n. This is the general formula for the probability distribution function for finding the expected value of a probability distribution. And if the probability is non-discrete, that is, if it is a function like this, a continuous function like this, then you just change this summation with the integration sign and you get the same thing. So that is exactly what they are doing here. This is the value, depth k plus 1, ki plus 1. It is the value and multiply by pi, which is the probability. So in total, it gives you the expected value. That is it. Bro, what are you doing? I am, for now, going through what is a optimal binary search tree. I'm seeing this for the first time myself, and we are trying to go through this together. And hello, good afternoon. And today is a contest. Are you excited? Today is a educational contest by the Cyprus University. and it is going to be cool. Educational contests are kind of hard in the sense that they are educational and they use some mathematical things or some graph things which are very unique. Yep, you are always up for contests. That is cool. And today we will have fun. Today is going to be a contest. Division 2. Cool. And now for this part. Figure 14.9a shows one binary search tree with expected value cost of 2.8, and this is the function for finding the expected value. And why this works? This works because of this. This is the formula. And for this, the expected value is 2.8, and they are somehow calling it contribution. They are calling it contribution. Why are they calling it contribution? That is a nice question. Why are they calling this contribution? What does that mean? For the probabilities given in the figure caption, part B of the figure displays an optimal binary search tree with expected cost of 2.75. Okay, finding the expected cost makes sense. This formula makes sense because it is a form of the general expectation value calculation formula. But what do they mean by contribution here? I guess let them cook. Yep, let them cook. Okay, shows one binary search tree. The first figure shows one binary search tree which has a expected cost of 2.8, and figure B shows another one which has a cost of 2.75. Okay, this example demonstrates that an optimal binary search tree is not necessarily a tree whose overall height is smallest. Okay, yes, that makes sense because the second tree has a higher height overall, higher depth overall, and this one has a lower depth overall, and the difference is by one level. But still, this one has a lower cost, this one has a higher cost. The expected value are different. Nor does an optimal binary search tree always have the key with the largest probability at the root. Okay, okay. Here key 5 has the largest, greatest search probability of any key, yet the root of the optimal binary search tree shown in K2, the lowest expected cost of any binary search tree with K5 at root is 2.85. Huh. Okay, so we have seen two things from this example. First of all, if we are making an optimal binary search tree, then the tree with the lowest height is not guaranteed to be the optimal binary search tree. Maybe there exists a tree which has a higher overall height and has a lower cost for searching with these given probabilities. That is the first thing. And the second thing is that the key which has the highest value, you do not always want to keep it at the root. Okay. You do not always want to keep it at the root because they are saying, and we can trust them in this book, they are saying that if we keep this K5 key, which has the highest probability, which we can check, the probability for K5 key is 0.2, 20%. If we keep this at the root, then the lowest cost that we can get is 2.85. 2.85. The lowest expected cost of any binary search tree with K5 at the root is 2.85. So if we keep this key with the highest probability at the root, the lowest cost that we can get is 2.85. But if we do not do that, if we get ourselves rid of that constraint and keep this K5 key anywhere we want, we can get an optimal cost of 2.75. That is much better than 2.85. As with matrix chain multiplication, exhaustive checking of all probabilities fails to yield an efficient algorithm, you can label the nodes of any tree with these keys to construct a binary search tree, and then add in dummy keys as leaves. And problem 12.4 on page 329, earlier problem, we saw that the number of binary search trees with nodes n is this thing, which is a Catalan number. Thus, you would need to examine an exponential number of binary search trees to perform an exhaustive search. We will see how to solve this problem more efficiently with dynamic programming. Okay, I guess we do understand the problem now. Okay, yes, so I'm always brain inbuilt intelligence cut earned intelligence by putting time. Yes, yes, because you might built in intelligence. Yes, you might be born with it, or you might not be, but you can always earn intelligence. And I think, yeah, there is 20% talent and 80% of our hard work. Yep, always hard work is going to beat the rabbit and the tortoise thing. And that is very hopeful. And you do not know before putting in the time if you are going to exceed. So you have to work with faith, and just with faith, work hard and believe that your time is going to pay off, but you do not know that in advance. So it is like a contract, a sacrifice. You are making sacrifice in the present moment, even though you do not know how it will pay off, but you have faith that it might pay off. And now, so we do understand the problem. The problem is we need to construct a binary search tree, and yep, and going through all the possibilities of constructing a binary search tree is not very optimal. So we are going to use a dynamic programming approach. I think if we apply those 4 steps of dynamic programming, we would be able to come up with something. And I'm not guaranteeing that I will be able to come up with a solution which works, but let's attempt, because this, I'm not very comfortable with graphs. So anyways, so what we have to do is find a way to optimal, find a optimal binary search tree, and that was very slow. Shit, that was actually very slow. Shit, my typing is very slow. Okay, and we know there are 4 general rules for solving a question using dynamic programming. Is define optimal solution, define what the optimal solution looks like, and second, define the optimal solution using solution recursively given optimal solution to sub problems. And then the third step is find the find the optimal solution. Okay, so what are we trying to do here? Let's first of all write down the variables and then the function that we are trying to optimize. The function that we are trying to optimize is the expected value function. This is the function that we are trying to optimize, and the variables with which we are working are, bro, you know about tourist, what a prodigy, bro. Yep, tourist is amazing. Gennady Korotkovich from Belarus, and right now his rating is very down. Jiangli bro has beaten tourist. Tourist has been at the top for more than a decade, but now he is at the 4th place with a rating of 3600, and brother Jiangli from China is at the top right now and very very close to a rating of 4000. And let me show you one thing. If you go to Wikipedia and search for Codeforce's rating, you see here from a rating of 3000 to 4000 you are a legendary grandmaster, but if you have a rating of greater than or equal to 4000 you are called a tourist. That is the title you get. So bro made a external title. Shit, there is a title on bro's name, so he is pretty cool. Yep, his highest rating is about 4000 and something, and it is the same at coders and at Codeforces. 4009. Shit, maybe Jiang Li might be able to beat it. I don't know what is his. Oh, he actually did beat it. Jiang Li got a rating of 4039 at some point, and Jiang Li is pretty cool. I have read his code and I was able to understand what he was writing, so that is pretty cool. And Tourist is also pretty cool. He's working hard. He wants to increase his rating. He was online 5 hours ago. He was grinding on Codeforces. That is cool. Bro just cannot have a higher streak than 5 days. And how many questions has Jang Lee solved? Jang Lee has solved about 7,000 questions, we could say. And Tourist has solved 2,000 something, 2,876. So yeah, Jang Lee has a overhead advantage, some would call it. Also, you know about Conqueror? I do not know about Conqueror of Tourist. I've heard that for the first time. Conqueror of Tourist. What is that? Conqueror of Tourist. Okay, is this guy trying to beat Mr. Tourist? Is that his goal? He has been at this since 2014, since Russia invaded the Crimean Peninsula. Is this guy trying to, and 2014 was the year when Facebook acquired WhatsApp, and also BJP came to power in India. And is this guy trying to beat Tourist? Is that his thing? He's from United States. That is cool. He has 2000 friends. He was online 40 minutes ago. Bro was grinding. That is cool. Yeah, he tried but failed. Lol. Yep. Shit. But he's trying, and I guess he will get better. He's already in top 0.01%, I would say. Legendary Grandmaster. Yeah, he's still very better. Very good. Now, so we do understand the problem, and yes, we were trying to make a dynamic programming approach of our very own to solve this. So this is the function that we are trying to optimize, and we can write a better form for this function. And before doing that, let's define the variables which we have. So we have, you can say keys, which is a list k1, k2, k3, dot 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 till kn. These are the keys. And then we have probabilities p1, p2, p3, p4, dot 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 till pn. And pi is the probability of lookup for the kith key. And this function, expected value function, this takes in the keys and the probabilities and returns a value. What we have to do? No, shit, we are not trying to reduce the expected value. That is stupid shit. No, we are not trying to reduce the expected value. We are trying to reduce the expected value, because here by expected value we do not mean shit. Yes, we do not mean the value of the key, but we mean the value so of the cost. So better name for this would be expected cost for these variables, and that is what we want to change. So we have the 4 steps for dynamic programming. Let's apply these in some way to find the solution. That the battle score. The battle score? What is battle score? They have 1-on-1, 1v1s. That would be cool. Having 1v1 with Gennady Korotkovich would be cool. E cost. So here we are trying to reduce this cost, and these are the variables. So first we have to define what an optimal solution would look like. Let's say we do have an optimal solution. Let's say, yep, let's just say we do have an optimal solution, and let's use not a general tree, but a tree with 4 values. Shit. K1, K1. That is not very beautiful. That is beautiful. Let's say we have 5 nodes. Yep. 3, 4, and 5. Let's say we have these, and yep. And let's also say, and their sorting order, since this is a binary search tree, let's say k1 is the smallest key, and k2 is a larger key, k3 is larger, and k4 is larger than that, k5 is the largest. And then they have some probabilities associated with them, and let's choose those. There has to be an order of the probabilities, and not just this shit, we also have dummy keys. We also have dummy keys which represent keys which are not present. They did 1v1. That is cool. This shows you cannot beat a talented guy who did hard work, no matter how hard you try. Also, look at Messi versus Ronaldo. Okay, if you want, yeah. So since that guy also has put in his hard work, and you are also putting his hard work, and that would be the case when talent is a factor, but that would be the case when you are putting in the hard work. And I guess most of us are not putting in the hard work, so that is not a worry that we have to worry about. We just work hard. And yep, so we have keys, but we also have mm, dummy keys. Let's call them dum, and they are numbered from D0, D1, D2, dot 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 till Dn. So we have the dummy keys. Dummy keys would be 6 in number, but let's say for now we do not have the dummy keys, and this is our own tree, right? Just like Donald Knuth says in concrete mathematics, take the simplest case first. So let's say we do not have the dummy keys and we only have these things, and we have to work with these and their probabilities. When we add p1 1 plus p2 plus p3 plus p4 plus p5, we will get 1. So we have to assign some values to these, and yeah, I guess these values would be fine. I think we do not have to actually use some values here, and we can work with these. But shit, there would be, let's see, yeah, let's say we do have a optimal binary search tree. Let's put k3 at the root because it is the median. K3 is at the root, and the things that are smaller than K3 are here, and the things that are larger than K3 are here. So this would be kind of our tree, one of the binary search tree that we could construct with these keys. And height, yep, their individual heights would be something. So we also need a function, or yes, we would also need a function which can take in a key and give us its height. So let's call that function h, and that takes in some key ki, and that function will return the height. Yep, that function will return the height. And if that is the case, then our expected value function, expected cost function, takes in k and it takes in the probabilities, and it will return the expected cost, which is going to be equal to summation manually drawing summation literally. It will be equal to summation of height for ki, height ki, this is I, height ki. Yeah, we are not going into the specifics, but generally this would be the thing, height ki into pi. That is what we are trying to summarize, and I goes from 1 till n, which here is 5, but I guess we can just work with the general case. So this is what we will have, and this is what we are trying to reduce to its minimum value. Okay, so if we are saying that this is a optimal binary search tree, then this subtree that we have right here, this subtree, it should also have the, it should also be optimal. Its cost should also be optimal when we are only considering K1 and K2. Why would it be optimal? Why should it be optimal? Let's say it is not optimal. Let's say this subtree, or also let me make the arrows. The arrows. Yep. And yes, so when we are considering this subtree, this one with K1 and K2, we are saying that if this whole thing is the optimal binary search tree, then this subtree should also be optimal, because let's say if it is not optimal, if this tree is not optimal, then its contribution here is going to be higher. But we want to minimize this thing. Therefore, in the higher binary search tree, when we are considering all the nodes, the value that we will get with this unoptimized binary search tree would be higher than the value which we could get if this tree, this subtree, were also optimized. And also, if we look at this, if we look at this function, this h thing and this pi and ki are always fixed. They are not changing. The only thing that is changing in all the binary search trees that we could make is the height function. And that is the only thing that is changing. And then when we look at a subtree, the height of the height function does not change. So when we are looking at the whole tree, or when we are looking at a subtree, this height function gives us the same height that it would, and the number of nodes that we are considering at a point does not affect this height tree. So all we have to do is change this height function. And yep, so we have at this point done the step 1. We are saying that if if we have an optimal subtree, optimal tree, optimal binary search tree, then all of its subtrees will also be optimal. That is how our optimal solution would look like. Now we have to define recursively how we could find our optimal solution using the subtrees, using answer to optimal subtrees. And that is going to be a bit tricky. Hmm. How could we go about doing that? Because we don't even have a order. Yes, we literally do not even have a order. Wait, we do have a order. Let's say this thing is empty. This thing is our best binary optimal search tree. And then when we are trying to construct something like this, we begin when we are trying to construct a optimal binary search tree, we begin with the empty tree and we do not actually know what to put there. So internally it is empty. We do not know which key to put there. So we have a bunch of choices and shit. Okay. So we could go with this node as the root. We could go with this node as the root. We could go with this node as the root. We could go with this node as the root of this particular binary search tree, or we could go with this node as the root for this binary search tree. Let's say we do go with this node and with this node, and this is okay. This is now everything is making sense and it is coming together. Like I said, at every step we have some choices and those choices give us some values. Optimal value, if I make the choice one, let's say it is A, and when I make the second choice on the optimal value that is returned to me is B, and yep. So when I choose K1 as my root, I will get some optimal value. When I choose K2 as my root, I will get some optimal value. If I have the answer to the optimal subtree that K2 would require, and I would have some value, some optimal value when I choose K3 as my subtree, and some optimal value when I choose K4 as my subtree. And that is cool. That is cool. Now, let's say, now how do I find the optimal values for a subtree? Let's say I choose K1. Let's say I choose K1 as my root. If I do choose K1 as my root, then the subproblem that this choice depends on is what is the optimal subtree that I can form using all of these remaining nodes. Now that is a good question we could ask, right? And which is just recurrence, which is a subproblem of the original problem, and this subproblem is of the same sort that the original problem is of. So let's say this thing gives us some expected value, right? Yep, this thing gives us some expected value, or before that we should write a function. Let's say we have a function f which says, which takes in the list of all the keys and yeah, list of all the keys, and then returns the expected cost for all of them. Yeah, it returns the best expected cost with those keys that we could get. So initially, when our original tree is empty, we do not have anything in our tree, we will call this function fk with all of these nodes, and then when we have made one of the choices, we will remove that node from our list and call the function again with these remaining nodes, and this function would return some value, and we need to find out what is the cost that we get when we choose ki as our root. So this function, we are supposing this returns the expected value of a sub of the best optimal subtree that we could get, arranging these remaining nodes in some order. That is actually this is better. Arranging these nodes in some order, this thing returns that expected value. But then how do we add this node's value to the expected value function so that we get the expected value for the whole thing? Okay, that is easy. Yes, but also the probability function is not adding up to 1 anymore because we are not adding p1 when we chose this. And like we saw before, that finding the cost for a choice, value of a choice, depends on optimal value for the dependent subproblems plus the inherent value of making that choice. Here the optimal value for dependent subproblems would be returned by the fk function. This thing would be this, and the inherent value of making that choice would be pi into the height of this thing, and height of this thing would be whatever subtree I get. Shit, height means in the opposite. Height is calculated from the root and not from the leaf. Shit, I messed up. I messed up in the way that I was calculating the value for a choice. So we have to patch that up. I messed up a little bit. So value of a choice would be expected value. Yep, like that. Height. Here we do not mean the height. Here what we actually mean is nodes from the root. Let's call it n r. nr returns the number of nodes that we take from the root. And therefore, this function that we call, this f function that we are calling, this not just takes in the keys, but it also takes in a integer value, let's say v, and internally the cost function that it is going to call will be a bit different than this cost function. The initial cost function is this, the original cost function is this, and since we have removed some keys, this is n dash. We are not going through all the keys. That and this nr. We have to define a base case. We have to define a base case. And I think this cost function would never be called. Yes, shit, this cost function would never be called. Our base case for this f function will return some cost, and using that cost, we would add the cost for making that choice, and with we will always be working with that, and yeah, we would always be working with that, and I think we will not never call this cost function, so we can remove that. So let's define this one for the base case, how a base case would look like, and that is the second part. Define the solution recursively. So recursive. Okay, light is miss. Wait, is the Wi-Fi okay? If Wi-Fi is okay, that is cool. Light was messing up. So we have to define our function recursively for the base case. Shit, light is messing up. Wait a minute, I'll be right back in a minute. Yep. I'm back. Now it is fine. Totally back. And now going back to defining this function recursively, we have to find some base case. And the base case would be when size of k is 1. So when we can say k dot size equals 1, that would be our base case. And let's go to some nice place other than this. A empty nice place like this. Okay. So this would be our base case when size of k is 1, when we have only one element in our subtree. When we have that, then the expected value, the expected first for this thing would be pi, right? pi, where I is the only node in this k list. But if that is not the case, if k dot size, if k dot size is greater than 1, then we have to find the minimum. And wait, I can do something better. Minimum yo, that looks much better. Find the minimum when we go through all choosing all the values in k one by one. So call f on, and since it is taking v, so pi v into v plus 1, v plus 1, because v is the count of how many nodes are there above this current singular node in k, and plus 1 because we have to go to the kth node also. So v plus 1, and we will find the minimum value when we call this f function with ki and v plus 1 values. Hmm. That is kind of nice. Yep, that seems kind of nice. Find the minimum. Yep. And what do we return? So when we are at a base case, we just return pi into vi plus 1. But when we are not at a base case, we find the value and then we have to do something with that value and the node that we chose. So we cannot just return this value. We have to do something with it, and that doing something would be like plus add to this thing, add to this thing, add to this pi into v plus 1 probability for this root. Shit, yes, that is correct. Seems correct. Plus p into v plus 1, pi into v plus 1. Yep, that is about it. I think that is the correct recursion function, recursive function. Yep, this is our base case, and this is the thing. This is our non-base case in which we will find this minimum value, and this would be our output solution. But we are not doing anything extra in this, so that we won't be able to build the solution in the fourth step. But right now we are not trying to build the solution, we are just trying to find the optimal value. That is what we will do in this. Wait, is my mic on? Yes, my mic is on. Shit, I thought no one is listening. Yep, so that recursive function is correct. Now let's try to find the time complexity for this thing. So yesterday we saw if we want to find the time complexity, average kind of time complexity, that would be number of sub problem multiplied by work done per sub problem. So here I would say work done per sub problem. So this is hard to calculate. How many sub problems are there going to be? There are going to be a lot of sub problems. I think we are going to go through all possible cases that are possible, and the time complexity would be n square. Shit, yes, because at first we have n nodes, right? If we draw the recursive tree, this node is dependent on n functions, n subsequent calls to its function, and each function is called with n minus 1 nodes. So this is the first level. And then secondly, each of these n minus 1 functions is going to make another n minus 1 calls. And are the subproblems going to overlap? Yes, a lot of subproblems are going to overlap. Yes, a lot of subproblems are going to overlap. Shit, yes, a lot of subproblems are going to overlap. But how many is a question? So we have to find how many unique subproblems there are going to be. Number of distinct subproblems. How many distinct subproblems are going to be? And if that is not a very big number, then it is cool. Then it is fine. Okay, we can look at this like this. When we have chosen a tree I think 2 power n is going to be the number of unique subproblems that we have. No, we need to find the number of combinations. Okay, what is going to be the combinatorics of this thing? So we will have trees of size n, trees of size n minus 1, trees of size n minus 2, trees of size n minus 3. And if we have a tree of size n, how many? Okay, we will not have a tree of size n, that would be our bigger problem. But we will have some problems where the size of our tree is n minus 1. How many distinct trees can we have whose size is n minus 1? We can have trees, n trees whose size is n minus 1. And how many trees can we have whose size is n minus 2? We can have n minus 1 trees. And how many unique trees are we going to have whose size is n minus 3, n minus 2? So that is just summation from n. And how many trees can we have whose size is? We are going to have n trees actually. Shit, yes, here we have removed 2 nodes. So what are the number of ways we can remove 2 nodes randomly? It would be n into n minus 1. This kind of like n square. And for this, n into n minus 1. For the second node, into n minus 2. Check. The time complexity is very bad. The time complexity is very bad for this recursive function. But since we do not have to invent everything, we can go back to reading and seeing how we did with this and compare this, our own solution, with what the book is saying and see who is stupid. And I guess I am stupid. Okay, for a given set of probabilities, your goal is to construct the optimal binary search tree. So step 1, the structure of an optimal binary search tree, which we gave on our own, and we said for optimal binary search tree, the subtree that it has, they also have to be optimal. That is the structure. To characterize the optimal substructure of optimal binary search trees, we start with an observation about subtrees. Consider any of a binary search tree. It must contain keys in a contiguous range. Contiguous range for some ij. In addition, why should it have? That makes sense. I cannot just choose any tree, any node at random. If I cannot choose any node at random, because this is a binary search tree, this is not just any random tree. So this is not just any random tree. So for the root, I have n total options, but when I have made one of the choices, so for the right subtree, I will have on average n minus 2 choices, and for the left subtree, I will have n plus 2 choices. which is kind of like n choices. Not even n. This is asymptotically n because I have chosen one node already. But yeah, the thing would be like this. Okay, and then if that is the thing, then the number of subproblems would be n square. The number of subproblems is going to be n square. That is much better than n power 4, which is the total number of subtrees that there are, the total number of ways to construct a binary tree. So n square is also good. So I guess our solution is good. This thing, our recursive formula seems to be good. And if this is the case, then we will also need additional information here. We would need ki, some key, which we chose as the root earlier. Yes, and yes, yep, yep, that is what we will choose. And this function will take some implementation changes because the next input that we give to this function will depend on this key that we just got. Let's say call it key R, the root key for this particular subtree, which has k nodes. So when we call this function again, this is going to depend on something. When we choose ki as our next, no, this subset that is going to change. Uh, Let's see. Now we can state the optimal contiguous. Why it must contain keys in a contiguous range. Why should it must contain keys in the contiguous range? That I do not understand. Contiguous. Why should it be contiguous? Ah, okay, let's increase the number of nodes that we have in this one. Let's take it up to 10. 5, 6, K6, 7, 8, 9, 10. 7, make this 8. Then we have ninth key, and then at the end we have key number 10. Now, this is what we have. Can I arrange this in a way in which a subtree does not have contiguous keys? And it would be nice to know that if we could. Let's say we have this node 6 at the root. Then let's say we have node 1 here and all the rest of the nodes. No, when we chose this thing as a root, then the tree is now divided into two trees. All the things that go to the left and all the things that go to the right. Okay. Okay, and these things will be contiguous because starting from this, the sixth key, all the keys that have a higher value will be on the right, and therefore they will be contiguous. And all the keys that are on the left will have a lower value than this, and They can be in a contiguous order. Internally, we do not care about how the tree is constructed, but at this level, we only care about the fact that on the left side, all the things are contiguous, and on the right side, all the keys are contiguous, and that is interesting. And because now, since this by induction, of course, this is correct because we have this thing at this case, and now we say when we are considering this subtree, the same thing holds. If we choose K3 as the next node, next root node, then this also divides the whole subtree into two sections, K5 and 4, which will go to the right, and K1 and K2, which will go to the left. And then internally, we could have something like this. This would be our tree. That is actually nice and makes sense. Yep. Just stalling? No, 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 no. Yep. That would be our binary search tree. And from this, using induction and stuff, we can see that any subtree of a binary search tree, it must contain keys in a contiguous range I to j. Yes, it does. Yes, it does, as we saw. So for some I and j, for some I and j. In addition, a subtree that contains I and j must have at least it leaves the dummy keys, these, at least must also have at it leaves these keys. Yeah, not at least, but at its leaves. These should be the dummy keys. Yep. Now we can state the optimal substructure. If an optimal binary search tree T has a subtree T dash, this is a dash, containing Ki to Kj keys, then this subtree must be optimal as well for the subproblem with keys Ki till Kj and with the dummy keys Ki minus 1 till Dj. Yes, the usual cut and paste argument applies with contradiction. If there were a subtree T dash dash whose expected cost is lower than that of T dash that we got, then cutting T dash out of T and pasting T double dash would result in a binary search tree with a lower expected cost than T. Therefore, by contradiction, optimality of T, therefore the subtrees should also be very optimal. Okay, that is true. So we know two things. First of all, first subtree should be optimal. That is one thing that we know. And second, each subtree has contiguous gears, contiguous, contiguous nodes ki till kj, comma, or is much better. Yep, that is the thing. Those are the two things that we have established on step 1, which is define optimal solution. And that is how we define our optimal solution. Our optimal solution in our optimal solution, each subtree should also be optimal. And second, that each subtree has contiguous keys. Okay, spelling for contiguous is wrong. Contiguous. UOUS. Okay, now it is cool. So those are the two things that we have established, and that is cool. Nice, pretty nice. Now, with the optimal substructure in hand, here is how to construct an optimal solution to the problem from optimal solution to subproblems. That would be the second step, but okay. With the optimal solution, with the optimal substructure in hand, here is how to construct an optimal solution to the problem from optimal solution to subproblems. Given keys ki till kj, one of these keys, say kr between I and j, it is going to be the root of an optimal subtree containing keys from the left and from the right. Shit, okay. So this is why is every problem very, very similar to the rod cutting problem. This is very similar to the rod cutting problem now, because before, when I was writing this recursive formulation, I was unaware of this fact that each subtree has contiguous keys. But now I'm convinced that it does. Every subtree has contiguous keys. And now with that knowledge, this thing seems stupid. This is, I just wrote this 5 minutes ago and this seems stupid now. So we can write another recursive function. Let's do that before we just read out what is written in the book. So our function will depend on ranges I, j, and something called height, I, j, and height. And this will be equal to something. Now we will have to establish a base case. Our base case would be when I equals j. That is, we only have a single node in our subtree. When that is the case, then what do we return? We return the expected value for this singular node. And the expected value for this singular node is going to be h plus 1 into pi, pi, because that is the only node that we have in our tree. And this is what we return. But if that is not the case, if we have j greater than I, strictly greater than I, not even equal to greater, because if it was equal to, we will call this function. But here j is greater than I, then we want to find the minimum value for a subtree. And what do we call internally? We will call this function again and again, and we will have a variable r. It will call this function and add. First of all, it will get the it will get the expected value, expected cost from the subtree plus the expected cost for choosing this current ith node, which would be h plus 1 into pr. Yep. And in this, we have r ranging. R is ranging over a range. So r begins from 1. R begins from I, actually. Okay, yes, I am stupid because there will also be the right subtree whose value we have to calculate. So I messed up a little bit. So we can like forget about messing up, and we can write this, and we will call this function twice actually, from r plus 1 till j. Yes, we want the minimum value for this, and R goes from I till R less than J till J minus 1. Yes, and that is a very good recursive function, I would say. And this is very similar to the matrix chain multiplication. Like it is almost the same. Isomorphic. These two problems are isomorphic, as one might call it. These two problems are isomorphic, the matrix chain multiplication and this problem of finding the optimal subtree. And shit, I just remembered something, that the matrix chain multiplication problem can be boiled down to putting brackets. BRACKS. The matrix chain multiplication problem can be boiled down to putting parentheses in a certain order, which give the minimum cost of scalar multiplications. We can do that. And this problem is can be boiled down to finding optimal way to make a binary search, like BST, which can also be boiled down to putting parentheses. These two are equivalent and therefore these are isomorphic. And why, you might ask? There is a thing called Catalan numbers, and Catalan numbers are the number of ways you can arrange a binary search tree of n nodes, and Catalan numbers also give us the number of ways that we can put n opening and n closing parentheses. So yeah, they are, these two things are isomorphic. So that is a cool, nice fact, side fact. And moving forward, this is the recursive function that we have created, and these two things are isomorphic. That is pretty cool. Given keys ki till kj, one of these would be the root, and also dummy. We are not thinking about the dummies just yet. We are just working with this for now. The left subtree of the root kr contains the keys ki and kr minus I. Yes, if we are considering the r, makes sense because r is the root which we have chosen. So r minus 1. Yep, rth root is not going to be considered. Rth node is not going to be considered. No. And the right subtree contains r plus 1 till j, and these would be the dummy keys. As long as you examine all candidate roots kr where I less than equal to r j, and okay, r will go up to j. R will go up to j when we are choosing the last one as our root makes sense. It will go up to j, and yes, but if it does go there, then this r plus 1 does not make a lot of sense. So while I greater than equal to j, if that happens at any point, then we'll do this. This would be our base case. I guess we don't have to call this function when we hit this. Yeah. So we can just do this. Mm. And yep, we will not call this function in certain cases, and we will also not call this function in certain cases, in the edge cases. When r is equal to j, we will not call this function, and when r is equal to I, we will not call this function because we would just be going out of range. As long as you examine all the candidate roots for r from ith till the jth root, you determine all optimal binary search tree containing ki till kr minus 1, and those containing yes, this would be the left binary search tree, and this would be the right binary search tree. Yes, true. You are guaranteed to find a optimal binary search tree. Yes, there is one technical detail worth noting about empty subtrees. Suppose that in a subtree with keys, this you select ki as the root. By the above argument, ki's left subtree contains the keys ki till ki minus 1, no keys at all. Bear in mind, however, that subtrees also contain dummy keys. We adopt the convention that a subtree containing this has no actual keys but contain the single dummy key di minus 1. Symmetrically, if you select kj, then the subtree, then the dummy that you have is dj. So we have to do some edge case implementation, edge case taking care of to fix that. Yep. When no actual keys are there, but only a dummy key is there. But in our example, which we have written right here, we are not considering the dummy keys. We are just going low for now because my graphs is not good. My trees are not pretty good. So we are going to work with this. Now recursive solution. And yep, recursive solution. And this would be very similar to this form, except we do not have the dummy keys. To define the value of an optimal solution recursively, the subproblem domain is finding an optimal binary search tree containing keys ki and till kj, where I is greater than equal to 1 and j is lower than equal to n, 1 indexed, and j is greater than equal to I minus 1, which simply means their difference is at least 1. Yes, that's which simply means their difference is at least 1. And their difference is not 0 at any point. Their difference is at least minus 1. Not difference, but j minus I is at least minus 1. Yes. Yeah. So when j equals I minus 1, there is just the dummy node di minus 1, but no actual keys. Yes. Let Eij denote the expected cost of searching an optimal binary search tree containing the keys ki to kj. Your goal is to compute EIN, the expected matrix, the expected cost of searching an optimal binary tree for all the actual and dummy keys. The easy case occurs when this thing is true, when the subproblem consists of just the dummy key, the expected cost of which would be the probability. Okay, so we are not sending in the values. Okay, We are not sending in the height. And sending in the height, would it not matter? Let's see. When j greater than equal to I, you need to select a root kr from among these ki to kj and then make an optimal binary search tree with keys from I to r minus 1 as the left subtree and keys kr plus 1 till kj as its right subtree. What happens to the expected search cost of a subtree when it becomes a subtree of a node? Okay, cool. What happens to the expected search cost of a subtree when it becomes a subtree of a node? The expected cost should become double. The function, the cost function is this. And when we say that this cost was calculated for some tree and now we are making that tree a subtree of another tree, then how will the cost for this thing change? I think this will become double because this will not become double. All of these values n are number of nodes from the root till the kith node would increase by 1. Would increase by 1. So what essentially happens is when we have when we are finding this from for range ki dot till kj, if we make this thing a subtree of another tree, then this expected new cost would be equal to the original cost that we got from this plus pi plus pi plus 1 dot I plus 1 is like the subscript pi plus dot pj, because this thing nr would just increase by 1. So that would be how the cost increases, and we can find this part very effectively using prefixes. So that is cool. Prefix sum would be nice to calculate that. And when j greater than equal to I, you need to select a root. Yeah, yep. The depth, yep. What happens to the expected search cost of a subtree when it becomes a subtree? Yes, this thing. And the sum of all the probabilities of the node which were in that subtree. The depth of each node in the subtree increases by 1. So from equation 14.1, 14.11, not 11, 11, the expected search cost of this subtree increases by the sum of all the probabilities in the subtree. Yes, increases by the sum of all the probabilities in that subtree. This subtree increases by the sum of all the probabilities in that subtree. For a subtree with keys ki till kj denote this sum of probabilities as yes, since there are also the dummy keys which we have to consider, and they go from I minus 1 till j. Thus, if k is the root of an optimal subtree containing keys ki till kj, we have expected value eij would be equal to pr, the probability for this number which has a height of 1 plus the expected value for the left side plus wij, the new cost, plus the expected value for the right side plus the new cost increase in cost, which is the sum of the probabilities for all these r plus 1 till j nodes r plus 1 till j nodes. As a result of making this subtree from I to r minus 1 and from r plus 1 to j, a subtree of this root node, which is PR, noting that hmm, that is also true. That is also true. The sum of all the probabilities. Yes. So we can rewrite this whole equation as this E I r minus 1 plus E r plus 1 comma j plus wij, where wij is the sum of all the probabilities for nodes I till j. I and j are included. And not just that, there will be dummy nodes in between from I minus 1 till j. So we add them too right here. We summarize their probabilities. The recursive equation 14.13, this one, assumes that you know which node kr to use as the root, but we do not know. So therefore, we will have to iterate for r from 1 to j. And if we are at one of the base cases, then we return the value, the probability for the dummy node. The E, I, J values give the expected search cost in optimal binary search tree. Yes, 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 yes. That is the definition for that function, Eij. To help keep track of the subtree of the to help keep track of the structure of the optimal binary search tree, define root ij for this to be the index r for which kr is the root of an optimal subtree. Huh? To keep track of the structure of the optimal binary subtrees, define root ij to be the index. Okay, this thing returns the index. So in a way, it is storing the answer. Okay, yes, this value is storing the answer to be the index r for which kr is the root of an optimal binary search tree containing keys ki till kj. Although we will see how to compute the values of root ij, the construction of an optimal search tree from these values is left as an exercise, the first exercise in this section. Okay. We will need root ij to construct the subtree structure after we get the value, and we will need eij to get the optimal value, which is the lowest expected cost that we are trying to find. Now computing the expected search tree cost of an optimal search tree. Yes. So we just iterate enij. Yeah, we can write a iterative solution or we can write a recursive solution. Yes. And I do not have the interface to interact with the binary search tree. So this is what we are going to do. At this point, you may have noticed some similarities between our characterization of optimal binary search tree and matrix chain multiplication. Yes, we did see some similarities. They both have to deal with Catalan numbers. We did saw the similarities for both the problems domain. The subproblem consists of contiguous index subranges. Yep. Yes. A direct recursive implementation of equation 14.14 would be just as inefficient as a direct recursive matrix chain multiplication algorithm. Instead, you store Eij values in table. In this table, the first index needs to run to n plus 1 rather than n, because in order to have the subtree containing only the dummy nodes dn, you need to compute and store e n plus 1 comma n. Yes, the second index needs to start from 0, because in order to have a subtree containing only the dummy key, yep, a subtree containing only the dummy key, we would like need something like 1 and 0. You need to compute and store E10. Only entries Eij for which j is greater than equal to I minus 1 are filled in. The table root ij records the root of the subtree containing kij keys and uses the entries for which 1, uses the entries for which I and j are between in this range inclusive from 1 to n. Yep. A root will be required when we want to construct the subtree, and Eij will be required when we want to find the value for that subtree. That is what we want. Now, one other table makes the dynamic programming algorithm a little faster. Okay, instead of computing the values of Wij from scratch every time you compute Eij, yes, we can use the prefix. We can use the prefix. Which should take this many additions, store these values in a table. That is a prefix. Or we don't even need to store this in a two-dimensional table. We can use a single dimensional table for this. Yeah. This you must compute n square values of Wij in a constant time each. The optimal BST procedure on the next page, this one, takes as input probabilities and Qi probabilities for the nodes, and Qi represents probabilities for the ith dummy node. Yes, there are probabilities for the dummy nodes too. That is good. And the size n, and it returns tables e and root. Yes, it runs two tables, e and root. We can use e to find the optimal value, and we can use the table root to find the optimal solution. Optimal solution. Yep, one of the optimal solution. From the description above and the similarity to the matrix chain order procedure in section 14.2, you should find the operation of this procedure to be fairly straightforward. The for loop of line 2 to 4, this one 2 to 4 is initializing the E and W. Okay, let's go through the code. Wait, that is very small, very, very small. For I, so first of all, this function is creating E, W, and root. W we need internally for increasing the processing time for our algorithm, and root is something that we will return, and E is something that we will return, which will contain the optimal values, and root would be used if you want to create the optimal solution. Now, we are first of all filling in the base cases. That makes sense. We can fill in the base cases. When we are only considering dummy nodes, it would be I to I minus 1. Begin at I and go up till I minus 1. And then the expected value would be Q, the probability for choosing the dummy node I minus 1, and also the sum of probabilities would be the probability for choosing I minus one dummy node. Then we say first we are considering subtrees of length 1. And when we are doing that, we will iterate our I going from 1 till all the subtrees where we could have a length of 1. So n plus 1 minus L, and j is on the other end of this sliding window thing. And initially we are initializing our expected value to be equal to infinity. And we also have our wij, which we will use here below. Yes, which we will use here below, and we can expect wij to be filled for everything up until this point. So we are just adding new stuff to our wij so that we are in constantly also improving or filling up wij table. And then we are changing this root. We could say we can choose our root to be equal to any of these trees, any of these nodes from I till j. I and j are inclusive, and we are finding the correct value. And if we find a value whose value is lower than whatever we have already chosen, which is eij equal to infinity, it is infinity at the start. And whenever we find a value that is smaller, binary search tree whose cost is smaller than the one that we currently have, then we first of all update our binary search tree's expected cost value, and also we update the root function to include that root r value, which gave us this optimal solution. And then return e and root at the end. That is nice. Now figure 14.10, which you saw above, shows tables ei, wij. Eij is where this is the one. This has e values, this has w values, this has values for the root. And the running time is n cube. Shows tables eij, wij, root ij computed by the procedure optimal BST, which is this one right here, which we went through just now, and the key distribution shown in figure 14.9 as in the matrix chain multiplication 14.9 before. Of figure 14.5, the tables are rotated to make the diagonals run horizontally. Okay. Optimal BST computes the rows from bottom up. Yep, bottom up, we are computing rows from bottom up. We are arranging length from n equal till length is going from 1 to n. And then optimal BST procedure takes n cube time. Just like matrix chain multiplication, it also takes n cube time, but this is still much better than the total number of Catalan numbers, the total number of nth Catalan numbers, which is like n power 4. So this is much better than that. And this is cool. This is cool. And now the exercises. That is pretty cool. But before we begin with the exercises, I would like to go to the washroom, and I will be right back in a minute. Yep, right back. I'll be right back. Right. Back, even though no one is waiting for me to be back, but I'm still back. And let's go through the exercises. So this thing is very this binary search tree, finding the optimal binary search tree is very similar to the matrix chain multiplication. The only thing that would have helped me at the start was this fact, this fact right here. It must contain every subtree must contain contiguous ranges ki to kj, where I and j are like this from 1 to n, ranges from 1 to n. 1 and n are inclusive. If I knew this beforehand, I think I would be able to construct this whole algorithm, and that would have been nice. So, but now I remember it. Now I know it, and now I am armed with this knowledge. So that is cool. That is cool. That is very cool. Now going to the exercises we have here. Shit, this was actually the last chapter. Status cool, longest sequence palindrome. Okay, let's do this. Write pseudocode for procedure. Construct optimal BST. Yeah, we can construct, and this will be very easy. We can look for range 1 to n, what is the root, and then when we find the root, we take that as the root, and then we look for the left subtree, what is the root for the left subtree. Then we call the function again with that, and yeah, yeah. Determine the cost and structure of an optimal binary search tree for a set of n equals 7 with keys and the following probabilities. And that is fine. We don't actually have to do this. This is fine. And I am cognitively, deliberately not writing code for this optimal binary search tree problem right now because I'm afraid. Shit, okay, I'm writing a code. I'm writing code which will take these things and it will return the answer. Okay, let's write some code. CD, DS, and DP. What do we have? Concept, DP, dynamic programming. And we are writing code for finding the optimal binary search tree and optimal bs.cpp. And internally, our function is going to return an integer, and let's call it optimal bst, and it takes a vector of integers called p as in probabilities, and vector of integers q probabilities for the leaf nodes, or you could say dummy nodes, and then two integers I and j. Our base case would be if j equals I minus 1, then we are at a dummy node, and the expected value for this would be I, be qj, would be qj. Let me increase the size a little bit. But if that is not the case, then wait, we are going to write a iterative solution. Yeah, we are going to write a iterative solution. So my bad for messing that up. So this will not take these I and j's. We will work with a vector of integers. You will call it tab, and the size. How are I and j going to range internally? P dot let's say int n equals p dot size and int m equals q dot size. So n, since I can become small, a- and these two things are very similar. M is just equal to n plus 1, so we don't need that. N plus 1 and n plus 1. Wait, my bad. This has to be comma vector int n plus 1. Now we need some initialization. I equals 0, I less than n, I plus plus. Yes, we need some initialization. Yep, and here tab two values. There are going to be two values, I and j. So where will I be and where will j? Yes, yes. I comma I minus 1 equals probability of I minus 1 of I. So we'll have I plus 1 here and I here. And we also need a prefix sum vector, which will take as one dimensional. Ref size size would be two dimensional shit. It would no, it doesn't need to be two dimensional. It doesn't need to be two dimensional. Nope, it doesn't need to be two dimensional. And pref I would give me the answer when I'm choosing node I, all the nodes till I. So this should be plus 1, and I think this should also be plus 1. Yes, and this would be Q, of course, and I would go to N. Yes, and then internally for pref I plus 1 would be pref I plus the two things now. When I'm not choosing any node at all, then Q0 ref I plus 1 equals ref I plus 1. Ref I plus P probability for the ith node since I am choosing it plus Qi minus 1. Nope, nope, that is wrong. Qi plus 1. Nope, that is also wrong. Uh, First of all, this should be n plus 2 and okay, what is the invariance? What is the invariance? Why am I being stupid? Okay. N is the size, P, yes, and N is the count, the number of nodes, the number of true nodes, not the number of dummy nodes. And this thing is going to give me the answer. Yes, when I am choosing nodes from index 0 till index n. So n plus 1, n is nice. But when I'm not choosing any node, that would also be one of the things that I could do. So that's one. And prefix n plus 1 because I might not choose some node or I might choose all the nodes. So the size becomes n plus 1 and also plus 1 because it is a prefix. So for pref 0, when I'm not choosing any of the nodes, it should be equal to the probability for the first dummy node. And after that, this thing is going to fill in all the values. Tab 0 when I'm not choosing any nodes. When I'm not choosing any nodes, the answer would be this is going up till n. The fact that this is zero indexed is kind of crazy. Tab will go up to n, then I cannot access I plus 1 because I plus 1, n plus 1, tab n plus 1 will give me segmentation fault. And qi is something that we have here. And I am only struggling right now because I haven't established any base properties here. What are the invariances in this loop? What does tab ij represent? And that is only a problem because I think I didn't understand the solution correctly in those particular cases. But overall, I do get the solution. But I will not look at the solution. I will do it on my own. That is cool. tab I plus 1, tab I. So how will our I change? 0 would mean I'm not choosing any node, and n would mean I am choosing all the nodes. Yep. So I want this thing to go from 0 till n plus till n. I want this thing to go from 0 till n, and that means there are n plus 1 elements in this. And the second one can go from 1 till n. The columns can go from 1 till n plus 1. We can do plus 1 plus 1. So what does tab I j means? Tab ij is the expected cost when I am using ki, k, ki dot 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 till kj. The expected cost when I'm using all of these things. The optimal expected cost. And when we have our root case, when j is lower than I, that is j equals I minus 1. That is as low as it can go. It will not go lower than this. When that is the case, it would mean I am not choosing any of the actual real nodes, and I am only choosing one of the dummy nodes. And the dummy nodes that I am choosing is j. J is the dummy node that I am choosing. And I can write this as tab I and I minus 1 equals the dummy node, and the dummy node that I am choosing is qi minus 1. Okay, that makes a lot of sense. And how low can I go? This I can go from 0. This I can go from 1 till n. In total, these are n things. So having this thing here is fine. And n plus 2 is also fine. This thing will range from 1 till n. 1 till 1 till n, and the other part, so minimum value of tab can be 0 minus, sort of like that, something like that, right? 1 and 0, which would be q0, and the maximum value that tab can have would be n minus 1, which would be q n. Ah, there is something wrong with this. N minus 1. This is not the maximum value that I can have. The maximum value that I can have should be n plus 1. Yep. So having there n plus 2 is okay. And the maximum value will go till n, should go till n. So we will have n plus 1 here, n plus 1 here, and the lower values here. This is here. Yep. Prefix. Then Okay, that is the invariance that we want with our table function. Now with the prefix function, prefix I, what should prefix I return? Prefix I should return q0 plus q1 plus dot 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 till plus q. Q represents the dummy nodes. Ith node I minus 1. Q subscript I minus 1. Is that correct? No. The prefix function would not work here. It can work here. It can if I modify it a little bit. So this thing, yes, plus P0 plus P1 plus P plus dot 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 plus P probability of I. And the minimum value for this would be P0. P0 is not good. Pi minus 1. I Yes, P0 would prefix 0 would mean prefix I would mean I'm using the first I nodes, and when I'm using the first I nodes, then this is the thing. This will go till I, and P will go till I minus 1. So prefix 0 is going to be the minimum value, and prefix n is going to be the max. Prefix I will have the sum of all the dummy nodes up till I and including the I prefix node. And yes, this would be the maximum value. This would be the actually maximum value. Yes. And we can think of this in this way. We have P1 here and Q0 and Q1, and then P2, Q2, P3, and then Q3. For each prefix I, let's say I, if I equals 0, we will just have this thing. When I equals 1, we will have this sum. We will have the sum. So when we have a range like this, I will for sure include all of these things. This would give me the sum till now. I will subtract all the sums till this point and I will add this part to get me the correct answer, and that is pref. I think we can initialize pref 0 before. Yep. Pref 0 equals q 0, which we have already initialized. I plus 1. But this thing will not go there. Yeah, this I plus 1. If I lower than n, only then equals laptop is going to die. But if I, the previous value plus q I plus p I minus 1. That is correct. And let me put my laptop on charge so that it does not die during the stream. Laptop is charging. That is good. That is good. That is good. That is good. Now we have our values initialized. So for int L equals 1, L lower than equal to n, L plus plus. L is when we are the length of the nodes that we are considering. I for int I equals 0 till I less than n plus 1 minus L and I plus plus. And int j will be equal to n plus 1 minus I. If we go less, if n is equal to 2 and L is equal to 1, will be same. Yes, true. Cool. Okay. This thing returns I minus j plus 1, where I and j are inclusive. So when we have I and j, we need to fill the tab table. Tab I, tab j equals, internally we will have a loop for int k equals I, k less than equal to j, and k plus plus. Initially, we will have tab I, j equals int max, and then for each value, we will have tab I, j equals minimum of tab I, j, which was comma the cost of choosing the current k as the place where we split. And will k be equal to j? Yes, k will go up to equal to j. I will start from 1. Yeah, I should start from 1. Yes, I should start from 1 because starting from 0 does not make sense. I should start from 1, which would mean when I'm choosing only one thing as my index, only one node. There are a lot of invariances which I'm not keeping track of. Anyways, till k minus 1, plus k plus 1 till j plus prefix of using all the nodes till j, jth node included, j plus 1. Yes, j plus 1 is fine, j plus 1 is fine, minus prefix I using the first I nodes, yes, plus q I minus 1. Yes. That is cool. That seems to be correct. And then see out tab the last value tab dot flag. Dot flag. Okay, what is the maximum I value that I am having at any point that I'm filling up? N plus 1. But internally I'm going till n. All the nodes plus one extra node does not make sense. Yeah, see out tab n when I'm choosing all the n nodes dot back, not dot back, no. I'll fix this. N from 1, 1 is included and n is also included. Let's see if I have any error. LSB start blank D. Okay, I do have a bunch of errors because I haven't included anything. That makes sense. Moving and include. Still have two errors, which are B, return tab N, tab 1, N, include IO screen, int main, and we'll have our vectors. The question that we solve, let's first solve for this, and I don't know if this is going to work, but let's just see. Shit. These are floating point values. Shit. Let's make everything a double. And what were the values in there? The value brackets. Substitute every space with a comma, the whole line. And for this thing, these are the values that we have. Substitute every space with a comma, globally. See out, optimal BST is the function. P and Q as inputs and R. Most probably it is going to fail. Optimal BST. Wait, doesn't even compile because C limits. LSP stop. Minus 0.2. Why would I get a negative result? Because this thing. LSP start plenty and infinity. How do you write infinity? Just write infinity. LSP restart and same spool. -2, that is completely utterly wrong. 2.8 would have been nice, but this hard-coded value. Yeah, so that is not the problem. Or the problem is more logical than that. Though it shouldn't be. I'm not even doing any minus here. I am only subtracting. Yes. Yes, I'm only subtracting things here, but it shouldn't be a problem. I don't know. I will have to look at it at some point. But now it is fine. Now it's fine. I do at least understand the concept, and I'm not really using this right now, so I do not have to beat myself up for not being able to write this correctly. Suppose that instead of maintaining the table wij, you computed the optimal value wij directly from equation 12.9 and line optimal BST use this computed value in line 11. How would this change the effect of asymptotic running time? Asymptotic running time would be same. It will not change. Canute 264 has shown that there are always root, roots of optimal subtrees such as use this fact to modify optimal VST to make it run in any square way. What is this? Has shown that there are always roots of optimal subtrees for all I and j in this range. So this means I am narrow downing on the search area, on the number of choices that I have, and directly calculating value for a particular choice be the thing. And yeah, I guess this is good enough. This is actually pretty good enough what we have done in this stream till now. And it's been 2 hours and 56 minutes, and I have been studying, learning about what is optimal binary search trees, how we can solve and find an optimal binary search trees given probabilities for different nodes. Yep, a way to find out the optimal binary search trees. So that was nice. And tomorrow, yeah, tomorrow we will be doing CSES questions. That is nice. All the CSES questions. That is all of these questions, at least as many as we can do. In tomorrow's stream, we will do as many as we can do, and then I will move on to completing the CP31 sheet. That would be nice. And now, yes, so now the practicing is the only part that is left for dynamic programming. And after that, pretty much my dynamic programming would be pretty cool. So that could be considered done in a way. And then I would also have to work on graph algorithms. My graph is very bad. I would have to work on graph algorithms and tree algorithms. I'm very bad at graphs and trees. There are also advanced graph algorithms, advanced graph problems. Only 400 people have been able to solve this one, only 900 people, 55 people. There have been only 55 people in history who were able to solve this question. And 97 did attempt, but only 55 triumphed. And so that might actually be the lowest. The problem that, okay, for this one, only 50 people were able to solve this one. Additional problems, part two, 50 people, 19 people. Shit, stick difference. 128 people have attempted this, and only 19 were able to solve this. That is crazy. Absolutely. You're given n sticks of length ai till an. You must make exactly k cuts to the stick so that the number of sticks becomes n plus k, because making one cut gives me one stick. After making the cuts, the difference between the lengths of the longest and the shortest sticks should be as small as possible. Your task is to compute the smallest possible difference for all the amounts. Okay, the cuts must keep the lengths of the sticks positive integers. You may assume that the sticks can be cut m times. Yes, m times. Wait, what? K times. When k equal to 1, if these are the sticks, when k equal to 1, I can make one cut on this string, this stick, and make it length 3, 4, make it of length 3, 4, and the minimum difference would be 0 and 3. Okay, that does seem like a tough question, not even dynamic programming tough. And for today, I would say that is good enough. That is good enough. We did all we went through all of this and how we can find an optimal binary search tree. That was good. I was unable to implement the solution, but it is still fine. It is still fine. It is still fine. I showed up. That is good. And therefore, for today, that would be the end of today's stream. And thank you for being here. Bye.